A simple and somewhat effective method of determining the convergence or divergence of a series is known as the direct comparison test. It uses a similar principle to what we saw in the proof of the integral test, that if we can show that something is bounded below by something that is divergent, then the series in question must also be divergent, or that if it is bounded above by something that is convergent, this series must therefore also be convergent. The direct comparison test starts with the idea that we have two series, both of which have positive terms, and one of the series is term by term smaller than the other. Term by term smaller. So if we line up a sub 1 and b sub 1 will be bigger, or at least as big. B sub 2 will be bigger than a sub 2. B sub 3 will be bigger than a sub 3, and so on. Naturally, that would make the sum of the series b sub n larger than the sum of the series a sub n, simply by virtue of adding larger numbers together. So what this means is that the sum of a to the n is less than or equal to the sum of bn. In this case, we have two situations that can arise. If the series b sub n converges, that is to say, it adds to a finite sum, then the series a sub n, being smaller than it, must also converge to a finite sum. On the other hand, if the smaller series a sub n diverges, that is to say, if it adds up to an infinite value, and the series b sub n is bigger, then the series b sub n would also have to add to an infinite value, and thus diverge as well. Now, please note that this is still limited. It is based on the idea that we can compare two series. And if we can show that the bigger series is convergent, then we can draw a conclusion about the smaller series. If the bigger series is divergent, we cannot draw a conclusion. Likewise, if we can show the smaller series to be divergent, then we can conclude the big series is also divergent. If the smaller series is convergent, then it does not provide any conclusion about the larger series. So it is limited. We have to be very careful in the choice of our comparison series. It has to be either bigger or smaller, and therefore has to have a specific relationship as far as whether it is convergent or divergent. For example, consider the series 1 over 2 plus 3 to the n. Now, the plus 2 in the denominator, if it wasn't there, this would be a very easy series to work with. Without that plus 2 in the denominator, this is a geometric series. It's a geometric series with r is equal to 1/3. Now that being said, the convergence of that is pretty clear. A geometric series does converge. The rule for the geometric series was that if r was smaller than 1, the geometric series converges. Now, what we're seeing here then is that we know this series converges. This will only help us if 1 over 3 to the n is the larger series. So we either need a larger series that converges or a smaller series that diverges. Since we know this series to converge, we have to show that it is the larger series in order for the direct comparison test to be of use. So what we need to do is compare 1 over 2 plus 3 to the n and 1 over 3 to the n. Now, this is not the most obvious thing in the world, so what we might start with, actually, is looking at the denominators in comparison to each other. 2 plus 3 to the n is certainly going to be bigger than 3 to the n itself. The two fractions, then, are reciprocals of these. The idea is that the larger a value is, the smaller its reciprocal is. So if 2 plus 3 to the n is the larger of those two values, then its reciprocal, 1 over 2 plus 3 to the n, is the smaller of those two values. So what we have shown here is the larger series is convergent. That fits the first conclusion of the direct comparison test. So we have shown that term by term, the series 1 over 3 to the n is larger. And since the larger series converges, it sort of forces the smaller series to converge. Again, this is something akin to what we saw in the proof of the integral test. Now, using the same series, using a slightly different series, let's look at the series 1 over 3 to the n minus 2. Now, again, that plus 2, or in this case, the minus 2, is all that makes this appear different from 1 over 3 to the n. However, in this case, we will find that 1 over 3 to the n is not a sufficient comparison series. So as we already said, this is a geometric series with r is equal to 1/3. So that the series converges. However, 3 to the n minus 2 is smaller than 3 to the n, and thus 1 over 3 to the n minus 2 is bigger than 1 over 3 to the n. So what we have here is a convergent series that is smaller. The problem is here is that the original series, 1 over 3 to the n minus 2, could be a bigger sum that is still finite. It could be a bigger sum that is still finite. But it could also be infinite. Because of that, the direct comparison test here is inconclusive. It is a limited test. It is based on the idea that we can find a similar appearing series that is easy to determine the convergence or divergence of. But it is limited in that whether the comparison series converges or diverges is only part of it. We also need to show that depending on whether it converges or diverges, it must therefore be larger or smaller than the original series. For another example, consider the series n, 1 over the square root of n. Oh, 1 over the square root of n plus 1. This is similar to the series 1 over the square root of n. Also known as 1 over n to the 1/2. This is a p-series. It is a p-series with p is equal to 1/2 is less than 1. Therefore, it diverges. Now, since this series diverges, we need to show that it is the smaller of the two series in order for it to be useful. To show that, we start with comparing the two denominators, the square root of n plus 1 and the square root of n, in which clearly the square root of n plus 1 is larger. Therefore, their reciprocals have the opposite relationship. So what we are showing here is that the larger series diverges. The larger series is the 1 over the square root of n. And if the larger series diverges, then it doesn't tell us what's going on with the smaller series. The smaller series might still diverge, just to a smaller version of infinity, or might reach infinity more slowly would be a better phrase. Or it might still converge to a finite number. So this is not a good comparison. This does not provide a conclusion about the original series. So it is not a good series to use for a comparison. However, we might choose to use something else. This is also less obviously similar, less obviously so, to the harmonic series. A P series with P equals 1 that diverges. Now again, it's not the fact that the original series diverged that was a problem, it was the fact that it diverged and was larger. If we can show that with this divergent series that it is smaller, then we're okay. So what we now need to do is, again, look at the square root of n plus 1 compared to just n. Now, at a very small value, they are actually, the square root of n plus 1 is actually larger. When n equals 1, the square root of 1 plus 1 is 2, which is larger. When n is 2, the square root of 2 plus 1 is larger than 2. But when n equals 3, that's where the n starts taking over. So as long as n is bigger than or equal to 3, then the n is larger than the square root of n plus 1. This is okay, even though the original direct comparison test said that it had to be true for all n. The fact of the matter is that as long as it at some point takes over that for the rest of the series, one of them is bigger than the other, the initial couple of terms are not going to affect the convergence or divergence. The P series, the harmonic series, if I take the first two terms off of it, it's still going to diverge. It's still going to sum to infinity. Taking a 1 and a 1/2 away from something that is infinite doesn't change it from being infinite. So it's still divergent even if we ignore those first two terms. Now, what that means, of course, is that 1 over the square root of n plus 1 is greater than 1 over n for n is greater than or equal to 3. So what we now have is a smaller series. The harmonic series is the smaller of the two, and it diverges. And if the smaller series diverges, that is, it adds to infinity, then the larger series diverges. So the direct comparison test is tricky. It requires the right choice of a comparison series. The most obvious choice may not work. We might need to get a little bit more creative and use a slightly less obvious series. But again, as long as we pick a series that is easy to determine the convergence or divergence of, and fits the correct requirements, either it's a bigger series that converges or a smaller series that diverges, then it will suffice. There is another test that we'll talk about in the next video called the limit comparison test, which is actually much easier to use and much more conclusive than the direct comparison test, because it does not require us to show that one series is larger or smaller than the other. Instead, it will compare the growth rates of the two functions. It will compare to see if the two series have terms that are decreasing at a comparable rate. We will look at that in the next video.